So last time we started talking about the Schrodinger equation for the harmonic oscillator. And you can give me an example of a classical oscillator, can't you? Like what system would be a classical oscillator? Think back to physics, and you like probably talked about it. Yeah, springs. Yeah, springs. So two balls attached to a spring, that'd be an example of an oscillator, or just the spring itself, or a pendulum, anything like that. So we set up a quantum system where what we said is okay, we had an oscillator, and this was 0, and we set it up in a potential that looked like this. So, and then this potential is going to, not infinity, on this side. So we're applying the potential outside of here. On the inside, we have a different potential on the inside. So we define this function, our potential function, way back here, something classical. Hey James. Something like this where we have kx squared. So that's a parabolic function, right? Hence why we have it that way. Thanks. So, and then we got to a point where, okay, we had to set up our Schrodinger equation. We started with something like this, where it always starts like that, right? So what are the two types of energies that we have in the Hamiltonian?
Potential and kinetic.
Yep, potential and kinetic. The kinetic is pretty simple. We've seen it a couple times already. So it's negative h bar squared over 2m. What do we have?
Partial x.
Yeah. Specifically, is it just this?
Oh, plus partial y.
Okay, yeah, that is true.
Partial z.
Oh wait, well we said we're going to combine this only for a 1D system.
Oh, okay.
So we have a 1D harmonic oscillator. So we're close there. What do we have to do with that though? Is it just the first derivative?
Second derivative.
Yeah, second. Okay, so there's the kinetic portion. And then we'll just put sine x in there. And then we needed the potential part, right? Okay, what's our potential going to be though? You're looking right at it. You guys are like, what are you dumb? It's right there. Yeah.
That was a trick question.
Yeah. It's right there. So, okay, and then we have psi, e psi. And that looks complicated. We didn't really want to deal with it, so what we did was we tried to set this up sort of like a polynomial. So if I have x squared minus 1 is equal to x, how would you try to solve this?
Move the x over and factor.
Yeah. So you get that, which I think there is a solution to, but maybe there isn't. Maybe there isn't. So yeah, that's what you would do. So we did the same thing in this case, and we ended up getting to this point where are we? We divided by h bar squared, we moved things over to the other side, or we moved this over to the other side, and we ended up getting squared plus 2m e h bar squared x squared sin x is equal to 0. And what that alpha is, alpha was just something we defined to be that. If you want to know where that came from, just watch the lecture that I'll put up today. Sorry, I thought I was going to get to it over the weekend. Spent way too much time coyote hunting and didn't get anything, but that's all right. So we got to that point. And then if you remember back to differential equations, there is a solution for something like this. It's actually a Gaussian.
Wait, is that an N?
This is an n, yep. And so the solution to this ends up being a Gaussian equation where we have e x, or psi of x, is e to the negative alpha x squared all over 2 times some function, and then this function f of x, that's actually a power series. So you have c0 plus c1, x to the first plus c2, x to the second, and so on. Okay, that's a quick rundown of the last thing that we did. If it's going too fast, that's okay. Just review that video. Okay, but now we run into a problem where we don't really know any of these coefficients. So how are we going to get those? So we're going to try to do that today, and we're going to actually get out the energy. So there are hidden energy levels in here that we'll figure out soon enough, but what are they? Now, from the postulates of quantum mechanics, there was something wave functions had to be. Shut that door because Dr. Bean's going off. But do you remember what wave functions had to be?
Continuous?
Yep, they had to be continuous, right? So what does that really mean?
For every x value, there's a y value, pretty much.
Yeah, that's a good way to reason through it. Okay, so that's true. What other things can you do to test if a function is continuous? You're going to say it.
You take the derivative.
Yep, you take the derivative. That helps you. What else can you do? Or how many times can you take the derivative? Yep. So if the first derivative and second derivative are continuous, most likely your function is continuous. There's probably some sort of math thing out there that says it's not true, but that's what we're going to go with. So we took this function then, we looked at the first derivative and the second derivative. We had to use the product rule and the chain rule like 5 times, and we ended up with this kind of ugly function. So the first derivative is negative alpha x, e to the negative alpha x squared all over 2 times f of x, where that was our power series, plus e negative alpha x squared all over 2 f prime of x. So we had to take the derivative of our power series of that. Then the even more terrible one, we had to take the second derivative. So you take the second derivative of that. You have the chain rule and the product rule everywhere in here. What that one looked like in the very end. Ex squared times 2 alpha x. Did we go all the way through that? Like, did we just take the second derivative and didn't simplify it at all yet?
No, we just took the second derivative.
Okay, we just took the second derivative. So let's go that one. Oop. We're going to erase that. We ended up with alpha squared, x squared. Where are we? Minus alpha e to the negative x over 2. Sorry, staring at stuff. There we go. Times f of x plus negative alpha x e x squared all over 2 f prime x plus negative alpha x e x squared f prime of x plus e negative alpha x squared f double prime of x. Oh my god, that's sinister and terrible. Can we make it any simpler?
Probably.
Yes, we can. Because I'm asking you one, right? too, looking at that thing, there's gotta be something.
Factor stuff
What's that?
out. Do you factor stuff out?
Yeah, we can factor some stuff out. Some terms are gonna cancel out, some terms are gonna combine together. Are there any terms that are gonna combine together?
Yeah, and those two.
Yeah, these guys, right? They'll come together. Anything else?
Wait, does it go to the F?
Oh, yeah, oops, it does go. Sorry. Should go further. There we go, now we got it all. I think that's it. So, what we're gonna get then. Actually, that should be an alpha, I'm sorry, it's not two. Of course, you have to have these Greek symbols that all look almost exactly the same. Okay, what else do we get? Then we got minus 2 alpha x e, and then we got alpha x squared over 2 f prime of x, and then we just have plus e and negative alpha x squared over 2 f double prime of x. Your guy. Okay, so that's what we have. Now, if we go back to the Schrodinger equation, let's so we're going to sub this into our original equation, just into the Schrodinger equation. Whoa. Jesus, man, he's had enough of that. Okay. And we're also going to sub psi x equal to e negative alpha x squared x, all into the Schrodinger equation. Okay, so what we really end up with, when we go back to like where we solved everything for 0, we have f double prime of x plus 2m h bar squared minus alpha squared x squared psi x is equal to 0, right? Okay, so we solve for this thing already. We have that. We're going to plug these into this. So we're going to take this big ugly beast, that goes in there, and then this function goes there. Okay, it's going to look horrible once we put everything into there, but then we're going to find that there are some rules of power series that are going to make our lives a lot easier.
We want the simplify one?
What's up? Yeah, we're going to plug the simplify one. Yeah, so we're going to plug all this stuff in here. All right, so let's get that simplified one. So we have alpha, actually we're going to need, we'll start here and we'll see where we end up. X squared, f of x squared minus, oh, did we solve everything for that last one? I feel like we're missing something on this tab word.
Okay.
Oh no, I was just down and distributed something differently. So I'm going to distribute this through each of these functions. Okay, so if you have to go through and erase, you can leave it as is, it'll be okay. So minus alpha f x, and we have 2 alpha x f x plus f double prime x. And we could actually have made this a little bit simpler. We could have pulled out this E alpha x, right? So we're gonna pull all of that out. E to the minus alpha x squared all over 2. Okay. So we got that. Then we got 2me over h bar squared. One second. Things everywhere. Yeah, it should be h bar squared. F of x. Wait. Oh, all that minus this guy, right? E x squared over 2 times f of x is all equal to 0. Whew. Okay, there are some things that are going to cancel out, which is going to be helpful. Some things that are going to combine together. Do you see anything that's going to cancel out?
X squared.
Mm-hmm. This very first term, right? That's going to go away because we had a subtraction over here, right? So those go away. Awesome. Can anything else go away or be combined together?
Can you combine the 2 and the h bar with
So this thing,
the negative?
yeah. So we're going to get those two together. Because we have e to the alpha x minus that, like that's all going to be multiplied in there. Then we have this term that's multiplied in there, right? Okay. Cool. So what do we end up with? What we really end up with in the very end is we end up with f del prime x minus 2 alpha x f single prime x. And we can also pull out this e to the alpha x, right? We can put it over to the other side. The nice part is we have 0 on that side, so it just goes away. We don't even have to worry about it anymore. So f prime x. Then when we combine these two terms together, we get 2me h bar minus alpha, right? And what's that going to be multiplied by? fx. Go. Okay, and all of that is equal to 0. Cool. So it looks really complicated. Now we're to something that's a little less complicated. So that's where we end up. Okay, now this is where we're going to go back and start looking at power series. We have to start looking at these functions in order to solve this equation right now, right? Okay. I promise you this is like one of the most mathematically intense things that we're going to do in this class. After this, we're just going to like say math, and we're going to talk about it. Okay, so since f of x is a power series, with the generic forms, so we have f of x. If we go back to our general form, we had c is 0 plus c1 x raised to the power 1 plus c2 x raised to the power 2, and so on. What's another way we could represent that? So if we're adding a bunch of things together.
Sounds right.
Yeah, we could do a dot product. We're going to leave that out for now. But we could do a summation, right? Oh god, there's a horrible sin. Better. I think that's the only Greek letter that I actually do well. I don't know why. Okay, so, and we're gonna go to infinity, we're gonna start n is equal to 0. Okay. Now, what's the mathematical form we can express this in? We're gonna have a constant, right? So, c sub n. What's it gonna be multiplied by then?
X to the n?
Yep, x to the n. Okay. So that's a common thing in there. If you look in your book, you can, I think it's right in the front page, you'll see that we have some of these in there. Okay, now we also have to get f prime, right? Okay. F prime of x. So if we took the derivative of this guy, what happens to this? Yep, that goes away. So that's 0, right? So we got 0 plus, if we take the derivative of this one,
C1,
yep, we get c1 derivative of the second one.
2C2X.
Yep. X. Yep. Plus, what else do we get?
3C3X squared.
Yep. Okay. So what's a way we could represent that as a summation? We're going to start at a different spot. Since this part is 0, let's start as at n is equal to 1. And we'll go to infinity. So what's a way we could represent that one then?
N C sub n x to the n minus 1.
Yep. Have you seen that one before? Or just cool? That's awesome. Then we'll have f double prime, right? So we take the second derivative of those. This one ends up being just a little more complicated. We'll just run through it real quick. We get n. Where do you think we're going to start this index at then?
2.
Yeah, 2. Go to infinity. And it ends up being n times n minus 1 c n x. What do you think our x is going to be raised to?
N minus 2.
Yep, n minus 2. There's another way we could represent that too. Do a different summation. We can start at n is equal to 0. We do n plus that, n plus 1. So do the n plus 2, x to the n. I should have had it. Was there plus here? Plus 1. Leaving stuff out. Okay, so we have those power series. Now what we can do is we can plug them into here and we can see what we get. Which is what we're going to do. Shouldn't have reversed that. That's okay. All right, so we plug them into that equation I just erased. So into equation. And then what we end up getting is the following. And 0, we have to have that second derivative first. So we're going to do the n plus 2, n plus 1, c to the n plus 2, x to the n, minus alpha x, n cn x to the minus n to the minus 1. Do that. Because we set our index to 0 to make this a little bit easier so we can have these two terms. Looking at this one, can we still do that if n is equal to 0?
Yes, because wouldn't it just make it all 0?
Yeah, you're right. So we could just set this n is equal to 0 because it's still going to work out because we have a 0 there, right? So x to the n minus 1. It's just kind of weird because most of the time you just wouldn't include n is equal to 0. But we want all of these summations to be the same so we can get them at that way. Okay, good catch. All right, so now then we have that part. We need that 2me h bar squared minus alpha, and then we have cn x to the n. And that's all to 0. Okay. Can we simplify anything, or is anything going to change?
You can,
There is something we can factor out, or that we're going to sort of change.
We can change the n plus 2 and n
What's this one?
plus 4, right?
No, can't change that one. What about this guy? You have an x out front, right? So if you have x times x to the n minus 1,
That's just X to the N.
oh, oops. So what's it going to be then?
X to the N.
Yep, x. So we're going to simplify that. So we're going to get the same sort of stuff out, except that's just going to be that. Okay, and that's actually kind of nice because it makes this, where we can discuss it in terms of even and odd functions. Cn plus 2x to the n minus alpha and c sub n x h bar squared plus alpha c sub n x sub n all equal to 0. Okay. So there's something else we could pull out of here. What can we factor out of this expression?
what's the C1 X3?
Yep. Can't get the cn because it's over here though. So there's a cn plus 2.
Excellent.
X to the n though, we can pull that out, right? Okay. If we put that over to the other side, it's just 0, right? So that goes away, which is nice. So really what we end up with is this guy. So we pulled that c sub n out. Now we need to get those coefficients. C to the sub n plus 2 and cn. So we have n plus 2, n plus 1, cn plus 2. We don't have to worry about that x to the n. Then we get negative 2 alpha n cn plus 2 me h bar squared minus alpha cn equals 0. We could combine these, but we're not going to worry about that right now. Okay, does that look right?
Where'd you get the 2?
You forgot the other ones.
I did forget any of the other ones.
It's one of the original version.
Oh, I just blew it. There's a 2 here. By the magic of math, there's no 2. Alright. Yeah, my bad.
That makes no sense.
Okay. So which of these should we solve for then? Or which of these is the most complicated in terms of the coefficients? So should we solve for cn plus 2 or cn?
The most complicated is CN, isn't
It actually ends up being cn plus 2 if you solve for cn. You could. Let's go with just cn plus 2 because that's what I did. If you solve for this, so solve cn plus 2, you get the following expression. Alpha plus 2 alpha n minus 2 n h squared all divided by n plus 2, n plus 1, all times c times n. Anybody know what type of relationship this is? You might not know it looking right at it. Do you ever talk about recursion relations in any mathematics courses? You might have called it something different. I'm going to make a big deal out of it. This is a recursion. Oop.
Yeah. So like the Fibonacci sequence and stuff.
Yeah. So really what you have to know is you have to know the first coefficient and the second second coefficient. And you'll know all the other ones. Because if you know this, you just plug in and you get it. Okay, so therefore, only C0 and C1 need to be known to get all the other coefficients. We need to know C sub 0 for the even numbers, because if we have 0 here, what's C2 going to be?
2.
Yep. If we have C1 here, what's this guy going to be? C3. So every time we have every time we have an even function, or excuse me, an even coefficient here, we're going to get an even coefficient for n plus 2, right? Every time we have an odd coefficient here, we're always going to get an odd coefficient. So we have an odd even thing. So C0 sub 0 for even, C sub 1 for odd, which ends up being helpful. Okay. Is that all we want to do? All right. So once we know these coefficients, we then know our wave function and we can solve for an energy. It is what we're always after. And then we'll look at other weird stuff related to it. Okay. So in order for our side to be bound and not infinite, some value of n, c to the n plus 2 must be 0. Because if we have a certain point where psi is infinite, it's not going to make any sense, right? Okay. So therefore, if we have this guy, we have c to the n, this should be 0, and we get all of this stuff. We have alpha plus 2 alpha n minus 2n e h bar squared over n plus 2 n plus 1 c sub n. Okay. So then what are we going to get out of this when we manipulate things through? Yeah, that can go away, and we can also get rid of that guy too. And we'll have an energy there. We'll have some alphas that we'll have to worry about, but we've gotten rid of those coefficients completely. So we end up with alpha plus 2 alpha n, 2n e, h bar squared is all equal to 0. Okay. Now this alpha, we conglomerated a bunch of constants in that line. Now, Haley, do you remember what alpha was? Or can you tell me what alpha was?
2 pi,
Yep,
nu,
yep, nu,
and
and h. Yep, what was, do you remember what nu was?
so it's a frequency.
Yeah, there's the frequency, so that's the frequency of our oscillation going back and forth, what it takes for a complete cycle. Yeah, we got the sanitarium going on back here. One day we'll all be able to breathe free.
This week out, they helped it.
Not enough alcohol to kill the bug, just enough to...
I don't know how.
That and the yelling.
Oh,
yeah,
yeah.
the yelling.
I lost your voice.
Yeah.
Talk.
How was was the crowd huge for Banas, or was it?
There were so many people there, I know. I did like, it was pretty big.
Yeah,
Maybe like 6 hours away.
wow. That's awesome. Did most of the student body go, or was it just a
I'd
lot?
say like 30%.
Yeah. There was a lot of people, like, it was cool though, because like, pretty much everybody was went, like, meet people.
Yeah, that's cool. Where'd you guys stay, or did you just drive back once you got done?
That was good.
Yeah.
It's like a holiday or something like that.
Okay.
Walmart.
One of those holes in the wall where like they don't even take a deposit; they just know the places it don't.
That wasn't that bad.
Oh, okay. Those are usually the places I stay in.
Yeah, 5 of us.
Ours had like 9 people in our hotel.
Grandfather once told me even cheap motels have their thrills. He's a good man. He also, in town, he had a garage, and the town wouldn't let him rip it down, so he broke a snake pit on the side and like broke all the windows out of it, and then they let him take it down.
That's awesome.
Yep, he's an awesome dude.
And then they're like, okay, I guess.
Yeah, well, fine. A little bit bipolar, but that's okay. So now what we're going to do, we're going to plug in for alpha, and we're going to try and solve and see what we get. So we have 2 nu m over h bar plus 2 times 2 pi nu m over h bar. We didn't have to add that squared, right? Nope. Okay, and then we had n, our quantum number in there, minus 2m e h bar squared is equal to 0. Okay, what are we trying to find right now? And, yeah, we want to find n,
Energy.
and we want to find energy. So we could separate this out, we could put n on the side, or we could try to isolate e. Let's try to isolate e right now. So we got to move this over to the other side, right? So we end up with 2 pi v h bar.
So we're just finding E first.
Yep, we're just finding e right now. We can take all of that junk out, right? And we end up with 1 plus 2n is equal to 2n e h bar squared, right? I don't know why I didn't make that parenthesis anywhere near the same size. There we go. Does everybody see what happened there? Okay. Screw something. No, I didn't. What's h bar again?
Oh, H.
Over 2.
2.
Yeah. So if we wanted h, h is equal to, geez, go math.
H. 2 pi.
Like that. Why did I do that? We'll see. All right, let's move some stuff around and see what we get. We gotta move that over to this side, so we get two, what's that?
Will the two pies cancel if you plug in the?
Yes.
But would you just plug
They
in each
will.
bar? No.
Yeah, I don't know why. Let's do this and let's see where we go. So you get M over H bar, then we gotta pull this stuff over, so we get 2M here. And the H bar squared.
Oh, and then one of the H bars cancels out, and then the other one will.
And then do I have 2?
So the one H bar will cancel out the H bar on the bottom, and then the other H bar will just be like H over 2 pi, and then the 2 pi's will cancel out.
Oh my god, this thing's wrong.
That's right.
Yes. Yep, there we go. So this that'll go away, that'll go away. There we go, M's go away. Okay, and then that's where we want to put this in. So we got pi, new H bar, or H, excuse me. 1 plus 2M equal to E.
I think it's still H bar at this point.
Yes, it is. Now we want to turn it into H, so we'll have a 2 pi. I know why we're doing this now. All right. So we plug that in, we get,
Should there still be a 2 over on the right also?
should there be? On the right.
No.
No, you got it underneath.
Did we?
Yeah, because that went
Yeah.
down there.
Okay.
I know why, it'll seem weird in a second. Squared that H1 plus 2N is equal to E, right? Okay. If we want to get rid of that 2 out front, here, we could divide that whole function by 2, right?
When you plug in H bar, isn't it H over 2 pi? So it'd be
H bar is H over 2 pi. Yes, you're right. There we go, that's what we were trying to do. Okay, so those pi's cancel out. We're left with frequency H over 2, 1 minus, or 1 plus. Yeah. And is equal to E. If we distribute that half through, we're going to get that, right? That's what the goal was.
you did it.
Okay, we did. Woo, we did it. Okay, we're N. What are the values N can have in this case? 0, yeah. 1, 2, and so on. From the way we initially set up our power series, we can have an N is equal to 0. Okay. This is kind of strange because, so now let's try to look at our potential, let's look at our model system. So we have our energy, we have our displacement in X. Here's our function. I'm gonna find something kind of weird. N sub 0. Or N is equal to 0 is along here. What's the value of E going to be for that system?
Half,
1/2?
U H.
Yep. Okay. Then we're going to have N is equal to 1. That one, what's that going to be?
1/2 U H.
How many halves?
So,
3.
Yeah. 3 halves. N is equal to H. What about N is equal to 2?
5 halves.
Yeah. oscillator, what do you notice about these energy levels?
They're all mu each away from each other.
Yeah, exactly. So this delta E here is always equal to mu h, which is different than what we had for the particle in a box, right? As n increased, that difference in the energy levels increase. So this is an important point that I think will show up now. The energy levels of a harmonic oscillator are evenly spaced. And this little difference here, we're going to talk about that next time. That's the 0 point. And we're going to discuss a little bit more what that is next time. However, we still haven't gotten a wave function. So next class, we're going to spend time getting the wave function. We're going to talk about what this 0 point energy is. And then we're going to talk about the kind of weirdness of this potential and how a particle can actually go outside of the potential, sort of similar to tunneling. Okay, are there any questions about that? Heavy mathematics day, I promise there aren't too many more of those left. No questions? Okay, I'll see you guys next time.